Hello, everyone. My name is Haiyan Liu. I currently work at University of California, Merced. So I'm the instructor of this workshop. This workshop focuses on the techniques used in analyzing a social network. The workshop has two sections. Section 1, we mainly focus on network fundamentals. Specifically, we will introduce you the concept used in network analysis. We will also introduce you one empirical network and explain the data structures. And at the end of this section, we will talk about descriptive network analysis. Now, in section 2, we will talk about network inferences. So we will specifically talk about the different models that we could use to analyze a network and to answer different research questions. Now we start with network concept. So what is a network? And what's the difference of network from traditional data structure? So traditionally, our data usually received as tabular matrices, right? And we have observation from on each variable, right? Now, what does network data look like? Now, a network is a data structure, and in this data structure, there are two primary components. One is node, the other is connections. So this is an example of a network, and there are bubbles. Those blue bubbles are nodes. And we also have gray edges connecting two nodes. Those are connections. Sometimes we also call them ties. Now, bubbles or nodes in a network usually represent some element or some social actors or some like Twitter account. And it could also be an item in a variable network. For instance, we could have instrument or survey to measure the personality, right? So therefore, each bubble could represent an item for personality. Now, connections in a network represent the dependence of the two ending nodes. For instance, if you in a college friendship network, those edges could be friendship. Now, in a Twitter network, those edges could be the following of each Twitter account. So in an atom network, those edges, for instance, could be partial correlations. So therefore, in overall, edges represent a certain type of dependence among those nodes. We can notice that, the network itself, the concept itself can be generalized to a very broad discipline. Now, based on the type of connections, we could have different types of network. Sometimes we only care about the presence or absence of connections between two nodes. Therefore, we only have binary relations. Now, sometimes we do not care about the direction of relations. Therefore, we have an undirected binary network. Now, sometimes the direction matters. For instance, when we collect friendship network data, we ask the students to report whether other students are their friends. Now, in this situation, right, a pair of students may read the other differently. One we may read the other as friends, but the other students may not. So therefore, the self-reported relationships usually are directional. So therefore, we will have a directed binary network. Now, sometimes the magnitude of relationships also matters. We care about different magnitude, different levels of relations. So therefore, we could have undirected weighted networks. So for instance, degree 4 relations is stronger than degree 3, right? So we may use a thicker edges to reflect the higher magnitude of relations. So if we care both about the direction, if the relationship is directional, and also the relationship has a different weight, then we will have a directed weighted network. Now, based on the types of weight and the types of direction, we may have different types of network. Now, subgraph is another interesting kind of a characteristic of a network plot. The smallest or most primary subgraph in a network is called a dyad. A dyad includes two actors or two bubbles as well as the potential relationship between them. For instance, this is a dyad with two nodes, and those two nodes connect to each other. Now, we could also have a dyad, right? Those two nodes disconnect with each other. Now, similarly, we could include the three nodes in a subgraph as well as the potential relationship among those three nodes. Now, this is an example of a triad with pairwise connections in an undirected network. Now, this is a triad with three nodes in a directed network. Now, both bottom network are rated as friends by the top nodes, for instance, and those two bottom nodes also connect. So this demonstrates the transitivity property of a certain type of relationships. So if those two nodes are both connected to the same common node, those two nodes also tends to connect. The last one is another example of a triad. So the relationship among those three nodes form a circle. Now, sometimes we also interested in a specific node as well as the friends, for instance, connecting to that node. So therefore, we're going to have a K-star type of subgraph. Now, in the first example is a K-star in an undirected network. So we have a common node. All the other nodes connect to it. Now, in an directed network, so the direction of the connection could start into the node we are interested in and then go outside to other nodes. So therefore, we have outer star. So we could also have in star where all the relations goes to the common node. So therefore, we could have different types of K-star. So those are just a few examples of subgraphs that are of interest to researchers. Now, by understanding those subgraphs, we may have more insight about the formation of social relations or connections within a network. So therefore, subgraph actually demonstrate the characteristics of a network. Now, researchers can use subgraphs actually as predictors to predict a network. For instance, we can count the number of K-stars in a network and also the number of circles in a network. And then we use those characteristics to predict the network. So there are other types of subgraphs of interest. For the time being, we use those few examples to give you some idea, right? Give you some idea. Cluster is another characteristic exists in a network. It's also a subgraph. Now, cluster, sometimes we also call it blocks or call it a community. So a cluster basically a subset of nodes. Now, within this subset of nodes, the connections are denser than connections with the rest of the network. Now, look at this graph. We have a cluster over here, and within this cluster, the connections are denser than across clusters. So we may have another smaller cluster over here and another kind of a cluster over here. Within each cluster, the connections are denser than across clusters. So the formation of a clusters is usually depends on the dependence among those nodes. Some nodes are more likely to connect to each other. So therefore, one one popular interest is to understand or explain the formation of clusters in a network. Now we talk about the data storage. How would we save a network data into a local PC? So we could save the network data using an agency matrix. Now, an agency matrix is a square matrix. Now look at this example. In this example, we have 5 nodes. So this is the network with 5 nodes, as well as the connections between nodes. Now, in an agency matrix, both the row name and the column name are the nodes. So we have 5 nodes, nodes 1, nodes 2, nodes 3, nodes 4, nodes 5, and the column is nodes. Now, each element in these matrices describe the relationship of the row nodes as 1 and the column nodes as 3. So therefore, the relationship or the connections between S1 and S3 is 4. Now, we could also get the relationship between S4 with S1 is 3. So therefore, each element in a position describe the relationship between the row actor, for instance, with the column actor. Now, we can also notice that in the agency matrix, the diagonal element is 0. This is because we are not interested in the relationship of a node with their self. So therefore, we just fill 0 there. Now, if you also value the self connection, therefore you can fill a different number here. For instance, you think that the self connection weight is similar to 1, then you can fit 1 here. But very often or usually we fill 0 if we are not interested in self connection. Now, the values in this tabular or in this agency matrix is different, right? We have 1, we have 0, we have 3, 4. This is because this is the relationship with the magnitude with a different weight. So the larger the number usually indicate stronger relationships. So agency matrix is a very effective way to save data, to save social network data. Now, in addition to agency matrix, we could also use edge list matrix. Now, edge list matrix basically we list the pair of nodes with connections. We put the starting node in the first column and the corresponding ending node in the second column. So therefore, in this example, it indicates that there is connections from node 1 to node 3. There is also connections from node 1 to node 4, connections from node 2 to node 4. Basically, we include all those dies with connections. So therefore, we exhaust, we put every pair of dies. There are connections between them. Now, if we also care about, or we also interested in the weight of a relationship, we could add a third column, which describes the magnitude of the relationship. So in an edge list matrix, basically we include all the dies with relations. And the start node is one column, the ending node is the other column. We just talk about a few concepts used in network analysis, right? We talk about what is called a network, what is a node, what is edge. We also talk about a few subgraphs, as well how could we save data in a computer. Now, in the following, I will introduce you an empirical data set, which is collected for college friendship network. Now, in this empirical example, we collect the data on a college friendship network. So therefore, we save the friendship network data in an agency matrix, right? Now, in this data set, we only save the data about the presence and the absence of friendships. So therefore, we have 0, 1 values. Now, we can also notice that the agency matrix is asymmetric. What does that mean? It means that, the student 3 rate student 1 is not a friend, so we feel 0 here. However, student 1 rate student 3 as a friend, we have 1 here, but we have 0 here. So this matrix is asymmetric. This is because we use a self-reported friendship data is directional. Now, in addition to the friendship network data, we also have demographic data. For instance, we have biological sex, we also have age data, we also have GPA data, and we also have smoking behavior data. Now, in addition to those data, we also collected personality data and mental health data, because personality closely related to friendship. Now, for the personality data, we use self-reported readings of personality traits. Basically, we provide a mini IPIP inventory to each student and ask the students to report their answers to each question. And then there are 4 items per factor, and it measures 5 dimensions of personality that uses Ocean model. In addition to personality data, we also collected loneliness data, happiness data, and depression data. And we are interested in how social network, how social relations in a network could actually predict happiness or predict depressions or predict loneliness, or those mental health data predict social relations. We basically would use to study both. Now, why do we analyze a network? Similarly to our traditional data analysis or analysis of a traditional data structure, we would like to tell a story out of a data set using statistical languages, right? Now, when we analyze a network, we also would like to tell a story about this network. We would like to unfolding the underlying black box of a network. Now, when we analyze a data, when we analyze a network, the first step, of course, we would like to describe this network, right? We would like to summarize the network information. So therefore, we need to do network plots. We need to talk about the network statistics. Now, after we describe the network, right, then we would like to understand the relationship of the network with other variables. So therefore, we first would like to explain which variable predicts the patterns in a network. And then we're also interested in how the network patterns predict behavioral data. So in different framework, network may play at a different position of a model. Network could be predictors to predicting other behaviors. Network could also be other than variable. We use other queries to explain the features in it. So therefore, in overall, we would like to include a variable in a statistical model. Now, next, I will first talk about descriptive network analysis. So we first talk about how could we plot a network in a 2-dimensional space. So network plotting. The first one is heat map. Now heat map basically plot the agency matrix. So they map each element in the agency matrix using a dot in the map. So a blue dot represents the presence of friendships in the friendship network. A gray dot means the absence of friendships. Now, by observing the patterns in the heat map, we can notice that there are 6 blocks. Now, within each of those 6 blocks, the blue color is actually darker. It means that there are more connections within those 6 blocks. So therefore, we have clusters. We have 6 clusters. So heat map plot is a very, very effective way to help us to understand the clustering properties in a network. Now, how can we obtain this plot? We can use the heat map function in the R package G+. And then we log the agency matrix, which in my dataset, I call it CF friend. So we could also plot a network by presenting the network diagram. So network diagram is basically we try to lay out those bubbles in a network or those social actors in a network in a 2-dimensional space. Therefore, how do we spread out those bubbles in a 2-dimensional space? We need some like algorithms. Now, those 4 network plots are the plots for the same network. Now, the first plot, or plot A, uses using an algorithm that randomly spread those bubbles in the 2-dimensional space. Now we can notice that those bubbles are more randomly scattered. Now the second one uses multidimensional scaling like algorithm. Multidimensional scaling is try to project those bubbles into some dimensions, which are going to maximize the similarity within each clusters. So therefore, we notice that these clusters is very, very denser. The bubbles stay very close to each other, and this cluster, the bubbles also stay very close to each other. Like these 2. So multidimensional scaling maximizes the similarity or closeness within each cluster. Now we can also tell the algorithm, tell the plot function to lay out those bubbles around a circle. And then we can also get other type of algorithm to help us to make decisions where to lay out those bubbles. Now, network plot is actually a very interesting topic, right? Different algorithms will achieve different patterns in a network plot. So therefore, yeah, it's very interesting to choose different algorithms to obtain different plots of the same network. We could also make the network plot more informative by including the external information either in the size of the bubble or in the color of the bubble. Now, for instance, in this plot, we use the blue bubble to represent a female students, and the red bubble represents a male students. By looking at the colors, we can observe the patterns among female students and among the male students. Now, in addition to categorical or binary information, we could also include the external information using a continuous scale. For instance, we could also reflect the happiness information in a bubble. So the larger the bubble here reflects the more happier that student is. The smaller the bubble, less happier. Now, the size bubble could also reflect the node degree. It's basically could reflect how many connections that a bubble has. So the larger the bubble, the more connections. So therefore, how to make your network plot more informative? We needed to have a well-designed plan. In the next, I will talk about a few network statistics that summarize network information. Now, the first group of statistics I will talk about is the centrality index. Centrality index is used to describe the position of a node in a network. So how important a node within that network. So there are different types of centrality index. They amplify different types of importance. So degree centrality, betweenness centrality, closeness centrality, and eigenvector centrality. So in the following, I will talk about those 4 centrality indices. Now, degree centrality is really about the number of edges connected to a node. Now, of course, depending on the direction of the connection, we could have in degree, which is the number of inbounds to that node. So we could also have out degree, which is number of outbounds of that node. So therefore, the in degree in a college friendship network is really about the number of the students rate student I as their friend. So the larger the in degree centrality means that the more popular that student is, because there are many other students rate me as a friend, so I am popular, for instance. Now, out degree is really about how many connections starting from the node we are interested in go to other node. So basically, it's how many friends I think I have. So this describes about the how outgoing or how influential a student is. Now, in degree and out degree will become the same in a n-directed network. So basically, if the relationship has no direction, then in degree and out degree will become the same. Now, we could obtain the degree centrality using the function degree from the SNA package. And then we just log the agency matrix in it. We can obtain both in degree and out degree. So the top is the histogram of the in degree, the bottom is the histogram of out degree of the college friendship network. We can notice that, the in degree tends to have large values, focus on larger values. It means that if a student is rated by other as a friend, is always tended to be a kind of many students going to rate them as a friend. So therefore, if a student is popular, usually it has many friends. Now, the bottom is out degree. It's relatively kind of flatter or more spread out. So some students has only a few friends, some has more friends. So it's kind of evenly distributed. Now we talk about the betweenness centrality. Now, betweenness centrality is another kind of measure about the importance of an actor. Now, however, we value an actor, we think an actor is important if that actor actually bridges the relationship of other actors. So this really means that we would like to know how often an actor involved in the shortest path of the other two actors. For instance, if we are interested in how actor I involved in the shortest path of the other actor J and K, we can first get the total number of shortest paths from J to K. And then we count among those number of shortest paths, how many involve the actor I we are interested in. So therefore, for each pair actor JK, we can get this proportion where the shortest path between J and K involved I. Then we exhaust all those pairs and we sum it up. Now we can think about that. If actor I is more important, therefore that actor should involve more often in the shortest path of the others, right? So therefore, BI should be large. So therefore, the larger the BI, the higher of the betweenness, the more important of an actor is. Now, for the betweenness centrality, we could also obtain in the R environment using the function betweenness from the SNA package. Again, we input the agency matrix, and we tell that we this is undirected network, for instance, then they're going to compute the shortest passes between any pair of nodes, and also compute the number of shortest passes involved the actor we are interested in. So we can obtain the betweenness centrality here. Now this is an example, small example about how do we get the betweenness centrality. Now if we look at the left example, right? Now for instance, we look at this top actor. How many shortest passes this actor involved in for the others? So this involved in 0 because this is really like the boundary of this network. And now how about we look at the second actor? Now we first look at any other pair of actors, for instance, this actor and this actor. How many shortest passes exist between the first actor, third actor? There is only one. Now, how many of them involve the actor 2? The one include the actor 2. So therefore, this contributed to the betweenness centrality 1 to this actor. Now, similarly, this actor also involved in the shortest path of the first actor with the top actor. This contributes another one. There's only one shortest path, and that shortest path includes the second actor. In addition, the second actor also involved the shortest path between the first actor and this bottom actor. And there is only one that shortest passes. So this contributes another one to the betweenness centrality. However, for the shortest path between those two nodes, and between those two nodes, none of them include the second actor. So it won't contribute to the betweenness of the second actor. So therefore, after considering all the possible pairs and all the possible shortest passes between those pairs, we got that betweenness centrality of the second actor is 3. And similarly, we can get that in this circle, right, network. The betweenness of any actor is 2. Now, this is demonstrated the betweenness of these 165 students. So on the x-axis, we just plot the ID of those 165 students, and also the vertical value or the y value is the betweenness of that students. We can notice that, some students have very large betweenness centrality, some have relatively smaller betweenness centrality. For instance, this student, right, or this student has largest betweenness centrality. It means that those students are important in terms of help other people to build connections. Now, some students have really betweenness centrality close to 0 or even 0. It means that student is rarely involved in the shortest path of the other two students and won't help build a friendship. Next, we will talk about the closeness centrality. Now, closeness centrality describes in overall how close a node to others in the network, to every others in the network. So, for instance, we can obtain the distance or the length of the shortest passes from actor I to actor J. Actor J could be any in the network. So we can compute the shortest path of actor I to any other actors in the network. Then we sum all those shortest passes. Now think about the denominator is the sum of all the shortest passes. The smaller means that the closer of actor I to any others in the network. So therefore, when we take the reciprocal, the larger the value is mean that the closer of actor I to others. So therefore, if a student have a large closeness index defined in this way, it means that a student is closer to others in the network. Now, here it is needed to emphasize that, the closeness index is not invariant. as network size n changes. So basically, if we have a larger network or a network with more actors, so the closeness centrality usually is smaller because the closeness path or the shortest path between any pair of actors tends to be larger. Okay, so therefore the closeness index is not invariant across network of different sizes. So therefore, probably it's unfair to compare the closeness of two individuals in a different network. Again, we can get the closeness indexes using the closeness function nested in the package SMA. Now, this is the histogram of the closeness of all students in the college friendship network. Student number 107 has the largest closeness. It means that this student is more central in terms of its shortest path to others in the network. Student 29 has the smallest closeness. So student number 29 is less likely, less close to other students in the network. So we talk about the different centrality measures, right? Degree centrality and the betweenness centrality and the closeness centrality. Those all try to describe the position of the network from a different point of view. Now, next, we will talk about eigenvector centrality. Now, eigenvector centrality is basically we use the eigenvalues or eigenvector scores to describe the position of an actor in the network. So this is in this formulation, the E is the eigenvector associated with the largest eigenvalues of the agency matrix. So we have an agency matrix, it's a square matrix. We could do eigenvalue, eigenvector decomposition. And then we found the largest eigenvalue is lambda 1, and its associated eigenvector is E. So therefore, we use the E, right? So we have a score for each actor. E is vector with n components if the network size is n. So for each node in the network, we actually have a value in the eigenvector E. We use those values to represent the centrality of that actor. Now, what does the eigenvector centrality mean? Now, look at the formulation, right? So the eigenvector centrality for node I is basically the sum of those centralities of the nodes who connect to actor I. So therefore, this sum of all those eigenvector centrality with those node J who connected to node I. So therefore, the centrality, eigenvector centrality of node I is basically the summation of all those centralities of their friends. Because, for instance, in college friendship network, right, we sum up those who connect to node I. Of course, penalized by the eigenvalue. So therefore, eigenvector centrality measures the importance of the friends of actor I. So if the friends eigenvector value here is larger, means that the friends is more important, their summation will also be large. So therefore, eigenvector centrality quantifies how important your friendship circle is. So if you make a friend with some very, very important guy, then you will also be important. So therefore, it's about how important your social circle is. This is especially very useful in political network, right? If you make friends with the president of the United States, probably you're going to have very, very high eigenvector centrality because you make friends with a big name. This is the histogram of eigenvector centrality. Again, student number 107 has the largest eigenvector centrality. Student number 20 has the smallest eigenvector centrality. We can notice that, for some students, is the different types of centrality measures have same rank, right? Consistent in rank. But for some other students, it's not. Now, we just talk about the different centrality measures. And we notice that sometimes give the same rank to the same node, but sometimes not. Now, how consistent of those different centrality measures? So therefore, we try to compare those different centrality measures. Now, we obtain the scatter plot, and we get the plot the trend, and we found that, the correlation, for instance, between degree centrality, and also the betweenness centrality is actually degree centrality, betweenness centrality is 0.8. That's quite large, right? And when we look at the scatter plot, we can notice there is a positive correlation. Now, when we look at the degree centrality and the closeness centrality, it also has a positive linear correlations, and the degree centrality and eigenvector centrality also have positive correlations. In overall, different centrality measures and give similar kind of ranks. Of course, there are individuals variations, or there are variations among different individuals, but in overall, they give a kind of a similar ranks about the importance of an actor in the college friendship network. Now, after we summarize kind of the network statistics, right? Summarize the node statistics, we actually can use the node statistics in the subsequent analysis. We could use the node statistics in a network as one variable or predictor in other analysis. For instance, in regression analysis, to predict the smoking behavior using the degree centrality. Now, this is the result when we use degree centrality to predict the smoking behaviors. Here, the smoking behavior we coded as 0 or 1. 1 means smoking, 0 means not smoking. And we found that, that the parameter estimate or the coefficient is positive, and which is significant. What does that mean? It means that more friends or the higher degree centrality, the higher chance to smoke, or the probability to smoke is higher. So therefore, actually, degree centrality predicts smoking behaviors. So here, what I want to emphasize that in many kind of network analysis, they first summarize network information and then use them in the subsequent analysis. We could also summarize the network information from the network level, summarize the information about the entire network. So network statistics. So we could describe a network by talking about the network size is basically about how many actors in a network. For instance, the college friendship network has 165 actors. So the network size is 165. Sometimes people also describe the size of the network by describe the total number of potential edges, basically count how many dies we could have. Now, we could also describe how dense the connections in a network is by talking about network density. So network density describes as the proportion of realized edges to the total number of potential edges. For instance, if the total number of potential edges in a network with 10 actors, right, is 10 times 9/2. And then we could count how many realized edges, how many actually connections in it. Then we get a network density. So network density is actually an index about how close a network is in overall. Now, different networks may have different density. The college friendship network we just introduced has density around 19.42%. It basically means that around 19% of the overall edges actually are realized. We could also talk about the transitivity of a network. Is basically this an index or degree about how nodes in a graph tends to cluster together. So we could define the transitivity by accounting what's the total number of triplets. A triplet is basically 3 nodes, as well as the potential relationship among those 3 nodes. We could also count about the number of closed triplets. So basically, the triplets there are connections between each 3 pairs of those actors in that triplets. So that's called closed triplets. So we account that proportion, then which is one way to define the transitivity. Now, when we have larger transitivity here, it means that, if 2 actors connect to the same common actor, then those 2 actors also tends to connect to each other. So this reflected the transitivity of the friendships. So in the college friendship network, the transitivity we obtained is 54%. It means that, about 50% of the triplets, they are close triplets, right? It also means that, if student A and B are friends with student C, so they are common friends to C, then A and B have a higher chance to make friends, which is higher than random chance. Random chance is 50%. So this reflected the chance for friends to make friends. Now, here is a comparison about the network density and the network transitivity of college friendship network and the team friendship lifestyle network. So, regarding the density, the college friendship network, the density is around 20%. However, for the team friendship network, which is quite low compared to the college friendship network. Now, regarding the transitivity, the college friendship network has a transitivity which is larger than 50%. And the team friend life network, which is around 30 to 40%. So different networks have different density and also shows different transitivity. So it really depends on the nature of the network. This is the quick summary of the code we used in plotting network, heat map plot, and the network diagram, and also the code used to extract different types of centrality index. We could also obtain the transitivity using the R function, which is listed here, right? So we can use the iGraph package and the transitivity functions. So this is the summary of section 1.